This is part 2 of Involutive Heegaard Floer homology and surgeries. This project is joint with Kristen Hendricks, Jen Hom, and Matt Stoffregen. In this talk, we're going to talk about several aspects of the proof of the mapping cone formula and the exact sequence, and we're also going to give a few practical details about the mapping cone formula. Okay, so the proof is somewhat analogous to the original proof that Ojvath and Szabo gave for their mapping cone formula. So let's review a few of the ingredients. The first ingredient in their mapping cone formula was a large surgeries formula, which we covered in part 1 briefly. This states that the Heegaard Floer homology of a large surgery on a knot, where the surgery coefficient is large, in the spin C structure Si, is quasi-isomorphic, or it's isomorphic to the homology of the complex A sub ik, the large surgeries complex, which is a subcomplex of CFK infinity. Now this only holds if n is sufficiently large relative to the Seifert genus of K, but it does provide a fairly useful computation for the Floer homology of certain three manifolds. And here S sub I is identified with I under the isomorphism between, there's a canonical isomorphism between spin C of Y sub n of K and Z mod n. The second ingredient in the proof of the mapping cone formula is a surgery exact sequence, which involves two parameters, n and m, and it relates the n surgery along a knot K and the n plus m surgery along K, and as well as y. And m is some positive integer. And here, this underline denotes twisted coefficients. And in the regular setting of ordinary Heegaard Floer homology, with twisted coefficients, you actually just get the direct sum of m copies of the untwisted module hf minus of y. And as in the previous video, the bold coefficients denote, the bold lettering denotes coefficients in the power series ring f adjoin u as opposed to the polynomial ring, which is needed for algebraic reasons, since we're working with hf minus. Okay, so I'm just going to try to communicate a few ideas that go into the proof of the involutive exact sequence, specifically the involutive sequence that appears here involving n and m, and I want to just talk about the case where m is equal to 1. So the main idea is that one wants to define a cobordism, or the first step is to define a cobordism map from the n plus first surgery of y along k to just y. And then the second step is to define a quasi-isomorphism between the n surgery, CFI of the n surgery, and the cone of this cobordism map. And there's always an exact whenever you have a mapping cone of any map, any chain map, there's always an exact sequence from homological algebra involving the domain of the map, the codomain of the map, and the mapping cone. And so if we can define a quasi-isomorphism from the Floer homology of yn to the cone of the map from yn plus 1 to y, that just gives us exactly the exact sequence we're looking for. So let's think about what actually it means to build a quasi-isomorphism, or actually just a map from the involutive Floer homology of yn to the cone of this map from yn plus 1 to y. What this actually comes down to, the natural way to do this, is to actually build what we call a hypercube of chain complexes. This notion can be found in Manolescu and Ojvath's integer surgeries on links. This is sort of they have a very thorough write-up of this. In our present setting, what this means is that we want to think of this diagram written here as actually a cube that's kind of missing two vertices. And we want to, along each edge of the cube, we want to define a chain map. And along each face of the cube, we'll define a homotopy between the two compositions along the face. And then actually this sort of length 3 map, this dotted map, is actually going to be a null homotopy of various sums of length 2 and length 1 maps in the cube. So what we'll do is we'll take the sum over all ways of composing a dashed and a solid line, and there are 4 maps, and then this dotted line is a null homotopy of that sum. Equivalently, we can just say that the total complex of this diagram is a chain complex. And the chain complex, you can think of it as having a filtration in the direct of by the cube. We have a filtration in each of these directions. And so the natural way to build this map phi is to start by building a diagram that looks like this. And actually, we want this diagram to have the property that the maps along the top coincide with the maps along the bottom. This is sort of what you will naturally get from if you try to build this. This is sort of the natural notion you're led to. And note that this isn't quite yet a map between involutive Heegaard Floer homologies. One particular issue is that we have iota along the vertical lines instead of 1 plus iota. So in the next step, since the maps along the top and the bottom agree, we can add the identity map to each vertical map, and the total complex will still be, or the diagram will still be a hypercube of chain complexes, or equivalently, it'll still be the total diagram will be a chain complex. So that when we do that, that looks like this. We've added identity, and I've also just added in these Q's, which don't really mean anything special. That's just kind of noting that's just notation. So we get this diagram, and now I've put some things as red and some things as blue, and that's because I can think of this now as a chain map from CFI of the end surgery to the cone of CFI minus, or the cone of the map from yn plus 1 to y. So the blue is the cone, and it's the cone of this cobordism map on involutive Heegaard Floer homology. So if you just stare at this, you'll see that this sort of cube diagram is exactly the same as a map from the involutive Floer homology of yn to the cone of this cobordism map. And so a lot of our paper is just centered on building this cube. And actually you get the fact that it's a quasi-isomorphism basically for free by just kind of some algebraic nonsense. Like this has a two-step filtration, the vertical filtration, and the associated graded is exactly Oshvath and Szabo's map in their exact sequence. That's just the map along the top. And that's a quasi-isomorphism. That's what they proved. And so you get for free from just very basic algebra that the whole map is a quasi-isomorphism. Okay, so that's kind of the that's kind of like a very brief overview of like the strategy that one would take to actually construct to prove this exact sequence. That's what goes into it. And now what I want to do is I want to transition to a slightly more practical overview of the strong version of the mapping cone formula, the one that we've proven that actually allows one to make computations. And also I want to sort of sketch, in the process, I like to sketch what this canonical model of the mapping cone, involutive mapping cone complex is. So just recall the weak version, which says that the end surgery along a knot is homotopy equivalent as an iota complex or as a complex over f adjoin u q mod q squared to a complex that has this form, where A and B are the chain complexes that appear in Oshvath and Szabo's mapping cone, and Dn is also the map which appears in their mapping cone formula. But then there are these, and iota A coincides with the knot involution, but we still have these maps Hn and iota B, which are still slightly mysterious to us. And we'll recall that the map Dn decomposes as V plus H, where V sends AS to BS and H sends AS to BS plus 1, BS plus N. That's what Oshvath and Szabo proved. That's just kind of recalling their previous work. But now, one thing that actually always holds as well is that Hn decomposes as J plus K, where J sends A sub S to B sub minus S, and K sends A sub S to B sub minus S plus N. And let me go back. Actually, this holds basically by the same proof that they gave, that Dn decomposes as a sum of these two maps. This is what it turns out to be. Okay, so now I'm going to sort of sketch how to actually... So if Y was an L space, so let's say S3, and we had a knot, and we knew iota K, I am going to sketch how to construct Hn and iota b to make this a cube. To make this an iota complex, or to make this to give the involution, these vertical arrows. I'll describe how to sketch. I'll sketch how this construction goes. So let Bs be as normal. This is sort of the subcomplex of C of k infinity, where you have I less than or equal to 0. This doesn't actually depend on S, but we added an S just as an index. Now Bs tilde, I'm going to let be the subset where J is less than or equal to S. Okay, this is a term that appears in the normal mapping cone formula. I don't think the notation with the tilde is standard, but I'm not aware of what the actual standard notation is. What I'm going to do is I'm going to fix a homotopy equivalence F from Bs tilde to Bs plus n. Now that exists just for purely algebraic reasons, because our complex has L space type. So let's just say it's a knot complex for knot in S3. Bs plus n and Bs tilde both compute the Floer homology of S3. So it's just F adjoint U up to homotopy equivalence. So there's always going to be a homotopy equivalence between those two. They're just the same object up to homotopy. Now V, I'm going to let be the canonical inclusion from AS to BS. That's just like in Oshlock and Szabo's mapping cone formula. And now the map H in their formula is F composed with V tilde, where V tilde is now the canonical inclusion from AS into BS tilde. So these are the terms that appear in their formula. There's nothing new here in what we've done. So exactly the terms that appear in their formula. But now we're going to investigate, here's a schematic. So we have AS. AS is kind of this quadrant where the vertical direction is, let's say, less than or equal to S. And there's an inclusion into BS and also an inclusion into BS tilde. Okay, and so now we're going to talk about how to construct H and iota B. Okay, and iota A. So iota A is actually, we're just going to set it equal to iota K up to a shift in the U power. I'm not going to write down what the shift is, but it's actually kind of easy to figure out. It's equal to iota K times a power of U. Let's say to map, just like to map the complexes to each other, following a specific convention. Iota B, I'm going to define it to be iota K composed with F. And this sends Bs to B minus S plus N. So that's what iota B is. And now we're going to investigate H. So it always decomposes as J plus K. And now the map K, which sends AS to B sub minus S plus N, I set that to 0. Actually, and that actually works in the formula. The component of the composition of the two compositions along the mapping cone that map from AS to B sub minus S plus N, they actually commute on the nose. So I can set K to be 0 and it'll work algebraically. And now constructing J is slightly more complicated. J sends AS to B sub minus S. And the way you do this is you first construct a map H, which goes from B tilde to B sub minus S, which satisfies that it's a homotopy between iota K and F iota KF. Now iota K and F iota KF, as maps from B tilde S to B sub minus S, are both homotopy equivalences. And since it's an L space type, like BS tilde and B sub minus S are both homotopy equivalent to FU, so and these both have the same grading, so they have to be chain homotopic. There's not enough room, so you just pick your favorite chain homotopy between them, H. Yep, such a homotopy always exists because Y is an L space. And then, without further ado, we just set H to be the composition H composed with V tilde, where V tilde is the inclusion map from AS into BS tilde. And sort of the important property is that of H, of this definition of H, is that we set K equals 0. And the really important thing is that J factors through this inclusion map. So it looks like we had a lot of choice. We could pick any map. It kind of looks like we could pick any map from A to B that's a homotopy making it commute, that relates the two compositions. But actually, that's not the case. We're picking one that factors through the inclusion map. That's kind of the key property here, is that it factors through the inclusion map of like AS into BS tilde. But you can pick any homotopy that factors that way. This algebraic procedure I sketch is like just this canonical involutive mapping cone. It's this one that's just kind of this algebraic operation that we described in the first talk. And so just to summarize, like this operation, what we proved is just that it always gives an iota complex. You take an iota k complex of L space type, it always gives you an iota complex, like this involution that we've constructed, kind of the vertical arrows in the diagram. They always square to the identity up to chain homotopy. And it's well defined on the level, it's like well defined on the level of homotopy types of iota k complexes and iota complexes, in the sense that if I have two homotopy equivalent iota k complexes, then the sort of canonical involutive mapping cones that we've constructed are also homotopy equivalent as iota complexes. So that's kind of probably the best one would hope for in terms of formalism. So in particular, in the concrete construction we gave, it's independent up to chain homotopy, or up to homotopy equivalence of this choice of f and this choice of little h. And then finally, probably the most involved part of this whole program is to actually show that this is sort of a canonical model of the mapping cone is actually homotopy equivalent to CFI minus of y sub n. So that's the conclusion of the talk. I'll go back to the last slide. So that's all I have to say. So thank you very much for listening.